Now we have one last section, which is a bit of I suppose an application of the concept of summing random variables. And it's not going to be anything really new, I believe. It's kind of more of a yeah, I suppose application or reformulation of the concept you already know. But in the actuarial literature, you pick up classical textbook, actuarial studies. They will often call a sum like that. Okay, they will call it the individual risk model, but it has a certain interpretation. Okay, so if you sum n random risks in this fashion, and okay, we use the same notation as before, S will be their sum. But where it is understood that the K's here, whatever you're summing, they represent different insurance contracts. Okay, and every XK then represents the claim on a specific insurance contract. Okay, and when you sum all of those, this is called the individual risk model, and it's a sort of a simple risk model where you just sum all the claims for a fixed number of contracts. Now, as a comment, this n here, it's fixed. It's assumed to be an integer that we know what it is. Later, we're going to see the collective risk model where this n will be allowed to be a random variable. But for now, n is just a number. Okay, so then this big S is then, of course, the aggregate, you can call it the aggregate loss, so the total loss incurred by the insurer, well, if the insurer is reimbursing all of those claims. Okay, and as I said, those individual XK, they represent individual claim amount on the whatever contract, the Kate contract here. Okay, hence probably why it has this name, the individual risk model, because you sum individual claims on individual contracts. And here, okay, so traditionally we assume those X's to be independent. Okay, now by the way, we talk a lot about independent random variable. A bit later in the course, we're going to deal with the case where variables might not be independent, but for now, it's a common assumption we make. However, they're independent, but typically they're not assumed necessarily to be identically distributed. Of course, they could, but here we have the flexibility that each X represent a different distribution. Now, also typically, those X's will be mixed random variables, and they will have a mass at 0. Okay, potentially a big mass at 0, because yes, most cases on a given insurance contract, there is a high probability that no claim is made in a given year, for example, or a given time period. So yes, the X could be a given XK could be 0 in that case. Now, because of independence, it's very easy to get the expectation and variance of S. So I'm not going to spend any time on this. As you know, expectation of S, or you don't even need independence for this, right? The expectation of a sum, independent or not, is going to be the sum of the expectations, of course, provided that the expectations are well defined, okay, are not infinite. For the variance here, you do need the independence assumption. By the way, this symbol, some sort of perpendicular sign, is often used to denote the independence. Okay, you need independence to say that the variance of a sum is the sum of the variances. But in the assumption of this model, we make this assumption, so then you can easily find the variance of S if you know the variance of individual contracts. Now, that's kind of a very simple model. Okay, there's nothing much new here. However, it's very common that within this model, we make one further step, which is the following. We decompose those X's in the following manner. We're going to say every X is going to in fact be represented as a IK times a BK. And now what are those things? IK is just a Bernoulli, so a 0-1 random variable with a certain probability PK. Now we denoted PK, and PK might, because we assume that those X's might have different distributions, so those PKs might be different. So P1 might be different than P2, than P3, and so on. And so it represents the occurrence of a claim for that specific contract. Okay, so IK would be 1 if a claim occurs for policy K. And then BK is a random variable representing the claim amount, so the claim size in dollars, or pounds, or whatever your favorite currency is. So the dollar amount or the money amount of the claim if a claim occurs. Okay, so you see that why we do this trick is because then we can model BK to be a continuous distribution, and that's quite practical most of the time. So you can model BK to be whatever, gamma, log normal, Pareto, whatever your favorite or most adapted continuous distribution is. But this yields that XK will be mixed, because if IK is 0, and this has probability, I suppose, 1 minus PK, well, then XK, of course, will be 0. So there will be a mass at 0. But then if IK is 1, so if there is a claim, then this claim is distributed as the continuous BK. Okay, I mean, BK doesn't have to be continuous, but often it will be. And again, typically we because it might be reasonable, but also it simplifies calculations. We're going to assume the independence of everything here. Okay, so all the i's are independent, all the v's, which also yields that the x's themselves are independent of each other. Okay, in this specific formulation, then you need to do a bit more work to find the expectation variance of the individual xk's as function of the mean and variance of this BK, which again, BK represents the size of a claim if a claim occurs. Okay, so just in terms of notation, if you denote mu k, the expectation of BK, and sigma k squared, the variance of BK, how can you find the expectation of xk and the variance of xk? It's not especially hard. Easiest is probably to use the law of total expectation and law of total variance. So expectation of xk, you can condition on ik. Okay, again, ik is the occurrence of a claim, of a positive claim. So here, this is just by definition. But now what is happening here? This bit, okay, remember that xk is just ik times bk. So expectation of ik times bk, given ik, given I know ik, well, that is you know, if you know ik, you can, maybe I can add the missing step here. You're gonna get the expectation of, okay, ik times bk, but knowing ik, it means I can put ik inside, sorry, outside of the inner expectation, and then I'm left with expectation of bk. Okay, and that's with expectation of bk knowing ik, but bk and ik are independent. So here, this doesn't change anything. So I'm left with this. Okay, and then expectation of bk is, of course, just mu k. Okay, and then, well, here it's reverse order, but ik is there and ik is there. So then you're left with expectation of mu k. Mu k is just a constant, and expectation of ik is pk. Okay, which should make intuitive sense. You know, there's the probability of a claim is pk. Now, if there's a claim, the expectation of that claim is mu k. So overall, the expectation of xk is pk times uk. For the variance, you have something quite similar. Again, let me just write here. Variance of, let me write this, variance of xk given ik, but remember, xk is just ik, whoops, ik times bk. Okay, but given here, given ik. Now, what's happening here? The variance of this thing, but knowing that I know ik, if I know ik, the ik here, conditional on knowing ik, is like a constant in the variance. So you can put it outside, but careful. If you put a constant outside, it's going to be squared. Okay, so in general, in full generality, you should have, this is going to yield ik squared times the variance of bk knowing ik. But again, variance of bk knowing ik is just variance of bk because bk and ik are independent. So knowing ik doesn't change anything in the bk, and specifically in the variance of bk. Okay, so then you can rewrite this, but here it's just ik squared. In this specific case, ik is just 0 or 1. So of course, ik in the specific case that it takes only values 0 and 1 is the same thing as ik squared. Okay, because 0 squared is 0 and 1 squared is 1 again. Okay, so ik is equal to ik squared, which is why here we can rewrite this as ik times variance of bk which is sigma k squared. Okay, and now we fall back to this thing here. Okay, which is technically, if you know, you could have a square here, you could have a square here, but it doesn't change anything because, of course, as I said, ik equals ik squared, because the only possible values for ik are 0 and 1. Okay, on the other side is the same thing here. We already established that expectation of xk, but given ik is going to be mu k times ik, and then we're pretty much done. Expectation of sigma square ik, well, the expectation of ik is just pk, and then mu k is that's just constant, so it gets outside the variance, it becomes squared, and then you get variance of ik. Well, variance of ik, remember, ik is just a Bernoulli, so it's going to be pk times 1 minus pk. Okay, we're done. This is the in this specific formulation of the individual risk model, the variance of a given xk is this, and the variance of a given, sorry, the expectation of a given xk is this, and the variance is this. And of course, if you want the variance and expectation of the whole S, you can just sum those individual ones. I mean, sum the individual expectations of xk's and the individual variance of xk's. Okay, now I get this one slide of explanation and then an example, and that will be it. But let's not rush, right? So that's all good for the moment, but now deriving the exact distribution of this S might be quite cumbersome. I mean, you can try. In some cases, you might have a nice result like the ones we've seen before, but probably you're gonna have a hard time to derive the exact distribution of S. So you could try to have approximations instead. So because S is just a sum of independent random variables, you might think, okay, if n is large enough, well, then I can use my central limit theorem to say that, okay, S should be approximately normal, okay? That makes sense theoretically, but of course, the central limit theorem applies if n is very large, and if, you know, in principle, it applies if the random variables are identically distributed. So in this case, they're not. Now, there's some version of the central limit theorem that work also when variables are independent but not identically distributed, but it's just a bit trickier. And so here, I guess the point is just that you might try a normal approximation, but maybe n needs to be pretty large for the approximation to work, okay, or to be reasonably good. Okay, and in our case, because we said that the x can be different, meaning have different distribution. If they're very different, okay, meaning they're very, yeah, they have widely different distributions with different means and different standard deviation. In particular, it could be that some accounts or some specific policies might have very large claims, okay. That might skew things, okay. That might mean that the approximation will take even more an even larger number of policies to apply. Because of that, it could be that other approximations, okay, so approximating approximating S not with a normal, but with a distribution that's already skewed and it has a longer or heavier tail than the normal, might be more appropriate, okay. Typical choices are gamma and log normal. Now, those are all comments a bit slightly vague. It's going to depend on the specific situation whether the approximation is decently good or not. But let's look at an example. So here, assume there's an insurer that has 300 fire insurance policies, but there's some heterogeneity in the policies. Okay, meaning 100 of those have a maximum claim amount of 100K. 100 of those policies have a maximum amount of 200K, and 100 policies have a maximum amount of 500K. Now, on every of those policies, the probability of a claim is just 1%. Okay, so this is always 1%. So every policy has 1% chance to claim, but the size of those claims is going to be different. So the claim amount for each policy is uniformly distributed between 0 and the maximum claim amount. Okay, so in the notation of before, this would be like saying that for k equals 1 for the first 100 policies, xk would be would be a Bernoulli. So the probability is always 1%. So the Bernoulli 1% times, so that's would be the IK from before, times, okay, so they're uniformly distributed. So times a uniform that is from 0 to 100K. Okay, so that's the first 100. And then the next 100, so for K equals 101 to 200. Okay, what you have is that the xk is then now is still a Bernoulli. Okay, the chance of a positive claim is still 0.1, but now it's a uniform between 0 and 200. Okay. Again, and the last 300 would be the same thing, but with a uniform that has a max of 500K. Now, first question: determine the expectation and standard deviation, SD for standard deviation, of the aggregate claim amount. And then what is the probability that claims are 3 times as large or more than their expectation, but using a normal and then log normal approximation. Okay, let's first start with the expectation and standard deviation. It's not too difficult. Okay, it's based on the formulas we saw. For one policy that is in the first category, meaning it has a claim size that is uniform 0 to 100K. Okay, the expected value of one specific is going to be the probability of a claim times the average size of a claim. Okay, this is just an application of this formula over here. Okay, 1% times the average size of a claim. So this would be expectation of xk. Okay, but careful for the k's from 1 to 100. Okay, but now you want the expectation of s. So there's 100 of those x's. Okay, so you sum 100 times this thing. Okay, this explains the 100 here. We put outside because every subgroup is the same size 100 here. Okay, and then for the same thing, this is 1% times the average size of the second block of policies that have an average of 100K in this case, because they have a maximum of 200K, and lastly, you add those with a max size of 500. Okay, and then you get to this mean expectation for S. Okay, for the variance, it's similar. Okay, you just apply the formulas over there. Okay, where you're gonna have this is the variance. Show you the variance here of what we call B before. Okay, the size of a claim given there's a claim. Okay, it's uniform, so it has this expression times here the P here, and then you have expectation squared times P times 1 minus P. Okay, which is what you have here. Expectation squared, blah blah blah. And again, you sum. There's 100 of those. Okay, there's 100 of those x's that have this variance. So you sum this 100 times. There's 100 with this one, and there's 100 with this one. Okay, hopefully there's no calculations mistakes here, and you get this standard deviation of 315K something. Okay, that's not too bad. Now for the approximation. Now, what the question is asking is to approximate the probability that claims are 3 times as large or more than their expectation. So as a mathematical statement, you're just looking for this probability that all the claims exceed 3 times their expectation. If you use the normal approximation, I think you're familiar with this type of calculation. Probability that S is bigger than this would be 1 minus the probability that it's smaller. Now S, you can standardize it, okay, by okay, of course, S minus mu S divided by sigma S is, of course, follows a standard normal. Okay, standard normal, I'm calling it here Z. Okay, of course, you apply the standardization on the other side as well. 3 mu S minus mu divided by sigma S, it becomes 2 mu S divided by sigma S. Mu S, sigma S, those are, of course, denoting the mean and standard deviation of our S. They're over here. So if you plug the numbers, you're going to get that it's the probability a standard normal is smaller than whatever this constant is. Okay, of course, this probability is pretty high, close to 1, but 1 minus this is going to give you a pretty small number. So based on the normal approximation, and of course, those you can obtain those probabilities with R using simply P norm in R of whatever this number is, or you can look at the standard normal table. So you get this number, it's relatively small, so it's, you know, less than 1%, like 0.55%. You know, this would be 0.555% if you want to express this as a percentage. Now let's do it again, but they ask us to use a log normal approximation. Now what does it mean? Well, it simply means assume that S is a log normal. What is the probability in that case? Okay. Of course, in this part here, we assume S is a normal. What is the probability in that case? Of course, it's not exactly normal. It's not exactly log normal. It's an approximation. Now, the first thing, just be careful with this. We say S is a log normal, but as of now, we don't know what the parameters of that log normal would be. Because, of course, saying that S is a log normal with parameter mu and sigma, those parameters, they are not the mean and standard deviation of the log normal. They're just parameters, okay? So what we do have, what I call mu S here and sigma S here, are the mean of S and the standard deviation of S. But they would not be equal to those mu and sigma that are, careful here, mu and what I call mu and sigma are the parameters of the log normal we use to approximate S, okay? I think that's clear, but let me write it just to make sure. If S is a log normal, with those parameters, expectation of S is not mu, and variance of S is not sigma squared. So the first step is to identify, by moment matching, what are those parameters mu and S? The parameters that yield that the log normal as mean mu S and as variance sigma S squared. Okay, where mu S and sigma S here, they are known. They are known because we derived them here. We know that the mean is 400K and the standard deviation is 315K. Okay, so the first step is just this. You have two equations and two unknowns to solve. You know mu S and you know sigma S squared. Now for the log normal, the mean is this expression of the parameters. Okay, careful again. Those, what is mu and sigma squared, are the parameters of the log normal. And again, same thing, you know that the variance, okay, and the variance, you know as a number what the variance of your log normal should be, but as a function of the parameters, it should be this expression of the variance. Okay, now here, two equations, two unknown. Probably the easiest way is to realize, okay, if I could take this sigma squared and I divide it by mu S, but squared, well, this squared, this expression, E mu plus blah, 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 squared, it becomes exactly this, okay? So if you take sigma squared, divide this one, this thing will cancel out, okay? And so only this thing will remain, okay? This explains the equation over there. Okay. Now, this is all a bit cluttered, but just make a second so you agree with this, that, okay, you take this, divide by this squared, this term is going to cancel out. What remains is this term. And that helps us because, of course, this is taken as known here. Okay, we calculated those things over there. So this is just a number, and then I can isolate what I need. Okay, because I'm looking for this fellow, I'm looking for this fellow here. Okay, and if you do the calculation, you get a numerical value for sigma squared here. Okay, and once you have sigma squared, then you can also take, for example, this this equation. Okay, you now know mu S. You knew it already. Now you know sigma squared. You can isolate mu. Okay, and you get this specific numerical value. Okay, you're almost done. Now you have the parameters of this log normal you use to approximate S. You can find the probability S, again, is bigger than its 3 times its expectation. 1 minus blah, blah, blah. Now you use the trick I presented in the video on the continuous distribution. If S is a log normal, you find easily the CDF of S evaluated at any number by just plugging the CDF of a standard normal, but evaluated not at the argument, evaluated at ln of the argument minus mu divided by sigma, where mu and sigma here are the parameters of that log normal. You do that, so you get to this calculation. Okay, and again, you can use R or the table of the normal to get a numerical value. And again, I guess the punchline here is that the number is pretty different. Okay, we had barely 0.55%. Now we have something closer to 3%. You know, we have 2.688. So it's quite different, and you see it kind of makes sense because the log normal is skewed, so it has a bigger tail. So here, it seems that the normal approximation underestimates the probability to be kind of big, to be much bigger than the expectation. Now, I say underestimate. In fact, as of now, we don't know which number is more correct, right? Because both are approximations. We get two substantially different numbers. This number is a bit closer to the real value. Now, what's the real value? We don't know, because we don't know the exact distribution of S. I think I'm gonna leave it at that for now, but I think a bit later I'll try to solve this problem with like a numerical approximation, or maybe simulations. Okay, and with simulations we can get a pretty good approximation of what the real value is, and we can see if it's closer to the log normal or the normal approximation. Okay, but we might do that a bit later, or maybe in a tutorial problem. Okay, I think that's enough for now. So I'll stop here, and thanks for listening. I hope to see you in the next video, or maybe in class next week. So thank you very much.